Imagine yourself cruising down a highway. You're going a steady 60 miles per hour. The car next to you seems stationary from your point of view, but is it really not moving? Relative to you, it might seem still. But relative to the ground, it's also zipping along at 60 miles per hour. This, my friends, is the essence of relative motion. Motion isn't absolute. It depends entirely on the observer's perspective. Your position and motion are always relative to something else. This concept, while seemingly simple, is crucial to understanding how the universe works, from the motion of planets to the behavior of light itself. In this exploration of the cosmos, we'll journey into the heart of relative motion. We'll unravel its mysteries and discover how it shapes our understanding of the universe. Fasten your seatbelts, fellow travelers, as we embark on this exhilarating adventure. To grasp the true nature of relative motion, we need to establish our vantage points. These vantage points, in the language of physics, are called reference frames. Think of a reference frame as a set of coordinates. These coordinates act like a grid, allowing us to measure an object's position and motion. We use reference frames every day without even realizing it. When you describe a car as moving forward, you're implicitly using the Earth as your reference frame. But what if you choose a different reference frame? Imagine observing the same car from a moving train. Now the car's motion becomes more complex. It might appear to be moving slower, faster, or even backward, depending on the relative speeds and directions of the car and the train. The choice of reference frame is crucial in physics. It determines how we measure and interpret motion. The beauty of physics lies in its ability to switch between these frames, providing a complete and consistent picture of the universe from different perspectives. Let's start simple, shall we? Imagine a single lane on our cosmic highway. In this one-dimensional world, objects can only move forward or backward along a straight line. Picture two cars, Car A and Car B, cruising down this lane. Car A is moving at 60 miles per hour, and Car B is trailing behind at 50 miles per hour. Relative to the ground, both cars are moving in the same direction. Now, imagine yourself in Car A. From your perspective, Car B seems to be moving slower, even though it's still traveling at a good clip relative to the ground. This is because you're subtracting your own speed from Car B's speed. Relative to you, Car B is only moving at 10 miles per hour. This simple example illustrates the core principle of relative motion in one dimension. An object's velocity is always measured relative to a chosen reference frame. Change the reference frame, and the perceived velocity changes as well. Our cosmic highway just got a whole lot more interesting. Let's add another lane, allowing our cars to move not just forward and backward, but also side to side. We've entered the realm of two-dimensional motion. In two dimensions, motion becomes a bit trickier to visualize. We can no longer rely on simple plus and minus signs to describe direction. We need a new tool: vectors. Vectors are mathematical objects that have both magnitude, size, and direction. We represent them visually as arrows. The length of the arrow corresponds to the magnitude of the vector, and the direction of the arrow indicates the direction of motion. Imagine Car A now moving diagonally across our two-lane highway. Its velocity is no longer confined to a single line. It has both a forward component and a sideways component. To fully describe Car A's motion, we need a vector that captures both of these components. This is where vector addition comes into play. By adding vectors, we can combine different components of motion to find an object's overall velocity relative to a chosen reference frame. Section 5. Vectors, the arrows that guide motion. Vectors are more than just arrows on a page. They are the language of physics, allowing us to describe and manipulate motion with precision. Imagine a sailboat navigating a river. The boat's motor propels it forward, while the river current pushes it sideways. To determine the boat's overall velocity relative to the shore, we need to consider both of these influences. This is where vectors shine. We can represent the boat's velocity due to its motor as one vector, and the velocity due to the current as another vector. By adding these two vectors together, we get a resultant vector that represents the boat's overall velocity relative to the shore. Vector addition is like following a treasure map. Each vector is a step in a particular direction. By following each step in sequence, we arrive at the treasure, the overall velocity of the object. Vectors are essential tools for understanding motion in 2 or 3 dimensions. They allow us to break down complex motion into simpler components and combine those components to find the overall picture. Section 6. Relative velocity vectors, navigating the sea of motion. Now that we're comfortable with vectors, let's dive into the heart of relative motion, relative velocity vectors. Relative velocity vectors tell us the velocity of one object relative to another object, which could be moving itself. We use a special notation to represent these vectors. For example, if we want to find the velocity of car A relative to car B, we write it as v sub AB. The subscript AB tells us we're measuring A's velocity from B's perspective. Remember our sailboat on the river? We can use relative velocity vectors to find the boat's velocity relative to the flowing water. This is different from its velocity relative to the shore, as it takes into account the movement of the water itself. Relative velocity vectors are crucial in many areas of physics, from analyzing the motion of planets in our solar system to understanding the behavior of particles colliding at high speeds. Section 7. A taste of transformation. The Galilean shift. Imagine observing a game of billiards from 2 different perspectives. One observer is standing still, while the other is walking past the table. Both observers see the same balls moving, but their descriptions of the motion will differ. The Galilean transformation provides a way to connect these different perspectives. It's a set of equations that allows us to convert measurements made in one reference frame to measurements made in another reference frame, moving at a constant velocity relative to the first. In essence, the Galilean transformation is like a universal translator for motion. It allows us to communicate and compare observations made from different moving platforms. While the Galilean transformation works perfectly well for everyday speeds, it breaks down at speeds approaching the speed of light. That's where Einstein's theory of special relativity comes in, but that's a story for another cosmic adventure. Section 8. Vectors in action. Adding up the pieces. Let's put our vector knowledge to the test with a real-world example. Imagine you're flying a plane from New York to Chicago. The plane's engine can generate an airspeed of 500 miles per hour, but there's a steady 50-mile-per-hour wind blowing from west to east. To reach Chicago directly, you can't simply point your plane due west. You need to account for the wind's influence on your plane's overall velocity. This is where vector addition comes in handy. We can represent the plane's airspeed as a vector pointing due west with a magnitude of 500 miles per hour. We can represent the wind's velocity as a vector pointing east with a magnitude of 50 miles per hour. To find the plane's overall velocity relative to the ground, we add these 2 vectors together. The resultant vector will have a magnitude slightly less than 500 miles per hour and will point slightly south of west. This is the direction you need to point your plane to counteract the wind's influence and reach Chicago directly. Section 9. Real-world relativity, from boats to planets. The concept of relative motion might seem like a mind-bending abstraction, but it has profound implications for our understanding of the universe. Consider the motion of planets in our solar system. From our vantage point on Earth, the planets appear to move in complex loops and spirals across the sky. This is because we're observing their motion from a moving platform, Earth itself. However, if we shift our reference frame to the Sun, the planet's motions become much simpler. They move in elliptical orbits around the Sun, governed by the force of gravity. The same principle applies to countless other phenomena, from the behavior of satellites orbiting Earth to the collision of particles in particle accelerators. Relative motion is woven into the very fabric of the universe. Section 10. Conclusion. Expanding our perspective. As we conclude our exploration of relative motion, let's take a moment to appreciate its profound implications. Motion, as we've discovered, is not an inherent property of an object, but rather a relationship between an object and an observer. This realization has revolutionized our understanding of the universe. It has forced us to abandon the notion of absolute space and time and embrace a more relativistic view of the cosmos. By mastering the concept of relative motion, we've gained a powerful tool for understanding the universe around us. We've learned to appreciate the importance of perspective and the interconnectedness of all things. So the next time you gaze up at the night sky, remember that the dance of the cosmos is a dance of relative motion, and with each shift in perspective, a new universe of wonder unfolds before our very eyes.